Hi everyone, how are you doing? Okay, great. So let's get started. Deepakashi is saying that feeling privileged to attend your live class. Thank you so much. Tejas saying good evening. Thank you. Good evening. Okay. So Deepakashi is asking, sir, how can I share my doubts with you? Uh, so Deepakashi, is this your first class? You can just type here or you can ask in the Telegram group later on. Okay. So let's just get started with the SVD. I mean, we have already seen some of this, but we will see more of the SVD today. More specifically, we are going to see these subtopics in the SVD, which are like this: rank of a matrix and a relation between SVD and how we can find out the rank of a matrix just by the SVD. Okay. See, SVD, this topic, singular value decomposition, this decomposition is so powerful. Let me just tell you, it is so powerful that whatever you study in linear algebra, that can be connected to a single value decomposition, whatever. Okay, maybe it is a change of basis, maybe it is a linear transformation, rank, okay, whatever you study in or maybe system of linear equation, okay, whatever you study in linear algebra can be connected to SVD. Okay, so anyway, let's just study this SVD further. So today we will see specifically how to find out the rank of a matrix using SVD, and why it is called singular value. I mean, it is very similar to say eigenvalue, right? So what is the way of looking at singular values just like eigenvalue? So right, that eigenvalue can be looked at like this. If it is a square matrix, then Ax equal to lambda x, right? Can we look at the singular value in a similar way? Which means, can we say maybe A into some vector, okay, maybe U or some vector equal to sigma, okay, maybe let's suppose A into Vi equal to sigma, which is a singular value into Ui. Can we look at the singular value just like the eigenvalue? Okay, we will see this. This is singular value. Okay, and then we will see that what are the relation of four fundamental subspaces with SVD, and how we can find out the basis of four fundamental subspace of a matrix using SVD. Okay, and then we will see tomorrow, we will see some more topics like geometry of SVD and little more topic, but we will see this tomorrow. Okay, so let's just get started with the SVD again. So as you know that SVD means singular value decomposition, which means a matrix A can be written as A equal to U into sigma into V transpose, right? A equal to U sigma V transpose. So here, let me just tell you here, this kind of decomposition is possible for any matrix. Okay, so this is, you can say, um, unconditional decomposition or non-restrictive decomposition. So let me just write it unconditional. Okay. So what do I mean by that? See, as you know, that we have already seen something called as eigenvalue decomposition, right? Eigenvalue decomposition. So what was that? We were saying that Ax equal to lambda x. That's what we know. If A is a square matrix, right? If A is a square matrix. Now we can also say A, let's suppose into U. U is a matrix of, you understand, U is a matrix of eigenvectors. Matrix of eigenvectors. Okay, equal to, or you can write it x lambda if you want to, equal to x lambda. This is equal to, can anyone tell me? This is equal to, yes, great. So Aditya is saying u lambda, yes, u and capital lambda, right? So this was also unconditional kind of thing, but the only condition is that A should be the square matrix, right? On top of that, suppose on top of that, this is possible. I mean, obviously it is eigenvalue, so eigenvalues are possible only for the square matrix. But let's suppose on top of that, u is invertible, or you can say u is having n linearly independent eigenvectors, suppose. Okay, then what we do, then we say that A equal to u lambda u inverse, isn't it? Is this okay to everyone? This is called eigenvalue decomposition or diagonalization, right? Okay. Now, do you remember that on top of that, if A is symmetric, then what we can do? If A is symmetric, then so this is if, right? If A is symmetric on top of that, then you can say A equal to, sorry, if U is symmetric, not U, A is symmetric, then in that case, you will be having orthogonal eigenvectors, right? So U will be, U inverse will be U transpose. So yeah, this will be if A is symmetric, then this will be U transpose, right? U lambda U transpose. This is what we have seen in the eigenvalue decomposition. But singular value decomposition is almost similar, but it provides more information than eigenvalue decomposition. Okay. It tells you many things. Okay, not just one or two, one or two things. It tells you many things. It will tell you the rank, it will tell you the singular values, it will tell you the four fundamental subspaces. So it tells you many things. So singular value decomposition tells you many things. So this was about eigenvalue decomposition, but now let's just see singular value decomposition. So when you talk about singular value decomposition, this is how it looks like. It is unconditional in the sense that there is no condition on A. Should A be symmetric? No. Should A be square? No. Right? So A could be anything, and you will be having this kind of decomposition. Right? Why this decomposition work? Basically, we have seen, kind of a sketch proof, which is also available everywhere, that we have found out that, okay, A transpose will look like how much, and A transpose A will look like how, right? So if you calculate this A transpose, how it will look like, or maybe let me first calculate A transpose A. It will be V sigma transpose and U, right? V sigma transpose and sorry, U transpose into A. A is U sigma and V transpose. So it will be, this is identity, I think, right? This is identity. So yeah, so it is V sigma transpose sigma, and then this is identity, this is sigma transpose sigma and V transpose, right? Okay. If V is orthogonal matrix, then let's just call inside matrix. Basically, it will be square matrix, right? Always it will be square matrix. Do you agree with me? This sigma transpose sigma will be square matrix. See, if sigma is m cross n, right? Then this will be n cross m, right? So it will always be square matrix irrespective of the dimension of sigma. So you can call it whatever you want to call, but it will be the diagonal matrix basically, right? So it will be the diagonal matrix. So basically the diagonal matrix, which is sigma transpose sigma, and then V transpose. So it looks like eigenvalue decomposition, right? So here, how to calculate this V? This V, you can say, are the eigenvectors of A transpose A. Okay. So V is eigenvectors of A transpose A. Similarly, if you calculate A transpose, okay, then you will be getting U sigma transpose and U transpose, something like this, right? Maybe you can try it out. I think you will be getting V transpose, V will get vanished, and then it will be sigma transpose and then U transpose. Yes. So you will be getting this, right? So how to calculate U? U is nothing but, since it is orthogonal vectors, so you can say U is nothing but eigenvectors of A transpose, right? And how to calculate this sigma? How to calculate this sigma? Basically, this particular matrix, right, is basically nothing but, in the diagonal, it will be a square matrix. Okay, whatever the dimension of sigma, let me just tell you, whatever is the dimension of sigma, okay, doesn't really matter. So for example, let's suppose it is m cross n. It could be rectangle, it could be, I mean, like spread it out, it could be like long matrix, it could be skinny matrix, whatever, right? But sigma transpose sigma will always be the square matrix. So basically, let's suppose that this is sigma 1, this is sigma 2, m rows, right? This is sigma m. Okay. And then after that, let's suppose like these are the zeros, okay? Doesn't really matter. So if you calculate sigma transpose sigma, okay, if you calculate sigma or sigma transpose, or you calculate sigma transpose sigma, actually both will be, no, both will, I mean, will not be same, but it will be, let's suppose if you calculate sigma transpose, then it will be basically square matrix, sigma 1 square, sigma 2 square, sigma m square, like this, right? And what will be the sigma transpose sigma? It will also be the square matrix, but this time it will be sigma 1 square, sigma m square, and then remaining will be 0. It will be of what dimension? N cross n. It will be of what dimension? M cross n. So basically, sigma could be anything, right? If sigma is like this, then sigma sigma transpose will be having sigma m square, and sigma transpose sigma will be having n cross n. You can calculate it n cross n, and then these are the entries, and remaining will be 0. Okay, in the diagonal, I mean, it will be exhausting, and then remaining will be 0. Okay, okay. I hope that is fine. So, do you recall that A, B, and B A share the same eigenvalue? Non-zero eigenvalues will be same, right? A, B, and B. So similarly here, these the sigma sigma transpose is basically these are the eigenvalues, and the non-zero eigenvalues will be same. Okay, remaining will be 0. Okay. Anyway, so what I'm trying to say here is that you can calculate u and v. So let's just do one exercise and let's just recalculate. I mean, we did it SVD yesterday, but let's just redo this. But before that, let me just list down all the rules. Okay, to find out the SVD. So SVD looks like this: u sigma v transpose. So what is the first thing that you will do? Can anyone tell me to find out the SVD? If you want, you can speak up. What is the first thing? Find A transpose A. Okay. Yes. Great. A transpose or A transpose it doesn't really matter. So let me find V. Okay. V is basically the eigenvectors of A transpose A. Okay. So as you can see here, V is eigenvectors of A transpose A. So find A transpose A, then calculate eigenvalues and eigenvectors, right? Okay. Is this fine to everyone? This first step, let me know. And those eigenvectors, you can say those eigenvectors will be U or V. Tell me. Will be V. Actually, it is also called right singular vectors. Okay. I mean, these are the eigenvectors of A or A transpose A. Obviously, A transpose A. Okay. So in terms of A, whenever we talk about A, we call them singular. Okay, instead of eigen. So which means here we call singular values, here we call singular vectors, here we call singular vectors instead of eigenvector. Okay. So we call it is also called right singular vectors of A. Okay. Right singular vectors of A. Is this fine to everyone? I mean, this is a name. Okay. This is just a name. Don't worry about it. Now, what is the second step? Can anyone guess? So we have got our V. We have just got our V. How to find the sigma? See, whatever the eigenvalues you had here, right? Whatever the eigenvalues you had here, now you basically let's just call those eigenvalues lambda. Okay. So basically, or maybe just for the name sake of writing, let me call them sigma 1 square, sigma 2 square. These are the eigenvalue. I'm intentionally I'm writing as an square in the sense that the eigenvalues will be in the form of sigma 1 square. I mean, if this is sigma 1, sigma 2 like this, then eigenvalues will be sigma 1 square, sigma 2 square. Okay. Or if you want, I can call them lambda if you want. Okay. So these eigenvalues are basically, you can say lambda 1, lambda 2, lambda 3, right? And so on. Yes. So what is the sigma 1? What is sigma 1, by the way? This is sigma 1, right? Sigma 1, sigma 2 like this, right? This is sigma. So what is sigma 1? Square root of lambda 1, isn't it? Similarly, what is sigma 2? Square root of lambda 2, like this, right? Like this, you can calculate the singular values. You have got your right singular vector. You have got your singular values. Now, what is the turn? The turn is to find u. How to find u? How to find u? Can anyone tell me? Yes. So basically, the third step you can say is to find u, right? Find A transpose and then ui's. Okay, so these are the three steps. Got it? Let's do some practice, and then we will see that the third step is not really necessary. Okay, third step is not really necessary. Okay, we will see that third step is not really necessary in the sense that we can find this use using some shortcut also. Okay, let's just see if there's a shortcut. Okay, let's just see. Okay. Do you want to do some practice? That do you want to calculate the vectors for this, which means that a is u sigma v transpose. Do you want to do by yourself? So what is a transpose a? Okay, let's just quickly see the a transpose at least. This is 9 12. Okay. I'm doing little cheating, but I hope that's fine. It's just a calculation, so I'm writing it. Okay, this is a transpose a. Okay, the eigenvalues actually are coming out to be 45 and 5. Okay, so eigenvalues. Now you tell me. Now you tell me. What is V here? Okay. Maybe I can also help with the eigenvectors. Mhm. Okay. A transpose. Sorry, this was A. I think I wrongly copied. Anyway, let me just copy from here. Okay. So the eigenvalues are coming out to be 45 and 5. Should I be telling you that these are the eigenvalues of A transpose or A transpose A? Or you can tell me that if 45 and 5 I'm telling you, then what does this mean? Since the dimension is same, right? Since the dimension is same, they will be sharing all the eigenvalues, right? They will anyway sharing all the eigenvalues, right? Since the dimension is same. Okay, so these are the eigenvalues. I think we are just yet to find out the eigenvectors of A transpose A, and then we will be getting our V. Find out the eigenvectors of A transpose, then we will be getting our U. And if those eigenvectors are not normalized, we need to normalize them, right? So let's just see the eigenvectors of, for example, A transpose A. Okay. So I think 1, 1 and -1 and 1 is the eigenvector. Okay. So eigenvector here, 1, 1 and -1 and 1. Okay. These are the eigenvectors here, 1, 1 and -1 and 1. And okay, let me also copy the eigenvectors here also. So 1, 3, -3 and 1. So here, the eigenvectors are coming out to be, right? If all of this information is given, can you tell me how to find out the SVD? I think you just need to normalize them. Then you will be getting your orthonormal vector. Just normalize them. You will be getting orthonormal vectors. These are the eigenvalues, which means make a square root of this. So square root of 45, square root of 5, right? And then you will be writing here. So u means this, right? These things divided by this its length, and then you will be writing this here divided by its length. Is this fine? Right? So this is how you can find out the SVD. Okay. So its length is 9 plus 1, 10. So that's why we are dividing by square root of 10. And then this is 1 plus 1, 2. So that's why we are dividing by square root of 2. Okay. Is this SVD fine to everyone? Now, have you noticed one thing? That they have done one thing. See, in this particular question, they have done one thing. They have calculated, the eigenvectors, as you can see, the eigenvectors of this A transpose A, they have calculated. But when it comes to U, they have not calculated it. They are doing something else, right? Okay, when it comes to you, they're actually doing some trick. Okay, we will see that trick also. So basically what I'm telling you, that the third step is not really very necessary. Okay, most of the time you can skip it. Most of the time, I will tell you how. Okay, so but before that, let's just have more practice so that you get to understand this SPD more. So suppose this is A, and then they are saying that compute the singular value decomposition of this particular matrix, right? So maybe you can do it. First, find out A transpose A, its eigenvalues. Okay, eigenvalues, eigenvectors, and then ultimately, I mean, you will be getting this as SPD. So basically, they have not shown the complete calculation, but yeah, you will be getting this as SPD. See, the eigenvalues here are 9, 1, and 4. So square root of them is 3, 2, and 1. Okay, and it is always a good practice to write those eigenvalues. Okay, in the decreasing order. Whatever is the highest one, write it first, then lower, then lower. Okay, cool. And the corresponding eigenvector will be here, right? Corresponding eigenvectors, corresponding eigenvector, corresponding eigenvectors. Okay. So I hope you can find out the SVD, right? This is the procedure. Okay. This is the procedure. There is nothing fancy here. It is just a calculation. Cool. So the SVD calculation might be okay, but let's just see more interesting things about the SVD. I mean, how to do numerically, that's okay. We will see some more tricks here and there, but numerically, most of the things are fine, right? Can you calculate A transpose A? Can you calculate, say, eigenvector, eigenvector, values? Can you calculate A transpose? It's eigenvector, right? So I think you can do it. So it is more like numerical calculation. So most of you people can do it. Now let's just see some more interesting things in SVD. And what are those specifically interesting things? Let me just tell you. See, these are the specifically interesting thing, which is that how to find out the rank of a matrix using SVD, how to view these singular values as eigenvalues, what is the relationship between the four fundamental subspace and the SVD. And then tomorrow we will see geometry of SVD, actually what it is actually doing, right? So in terms of geometrical interpretation, what it is actually doing. So, but today let's just do this. Okay. So let's just see how to find out rank of a matrix using SVD. But before that, all of you just need to confirm me that have you understood this particular, steps? Is there any problem with these steps that I've written here? Let me know. Okay, Tejas, I will answer this. Okay, I will answer this. First, let me know if this is fine. Okay, so these steps are fine, right? Great. Now, let's just see that how to find rank of a matrix using SVD. Okay. But before that, let me just ask you one question. What is the relationship between rank and eigenvalues? Suppose if lambda equal to 0 exists, or maybe let's suppose lambda is not equal to 0 for any eigenvalue, right? Suppose A is n cross n matrix. Suppose A is n cross n matrix. Now you tell me what will the rank of the matrix? If lambda is not equal to 0, then I can say then rank will be just n, right? Rank will be just n. Great. Now let's just see the second case where lambda equal to 0 exists. Okay. Lambda equal to 0 exists, suppose. Let's suppose you don't know, or doesn't really matter much, but let's suppose you know that lambda equal to 0 is repeating two times. Suppose repeating two times. Okay. Suppose repeating two times. Or maybe just repeating one time. Okay. Let's suppose it is repeating one time. It is not repeating two times. Or maybe whatever you want to do. Let's suppose it is repeating one time. Okay. For example, we can do it two times, but for example, it is repeating one time. Can anyone tell me? Can anyone tell me how many linearly independent eigenvectors will be there corresponding to lambda equal to 0. If it is just repeating one time, then 1. Great. Okay. If it is repeating two times, then yes, great. So if it is repeating two times, then you don't know, right? Maybe one linearly independent eigenvector, maybe two linearly independent eigenvector. So basically, this is called this is called arithmetic multiplicity. So this arithmetic multiplicity, as you know, it is what is the relationship between geometric multiplicity? It will be always lesser than equal to arithmetic multiplicity, right? If it is 2, then the number of linearly independent eigenvectors may be 1, maybe 2. Okay. See, what I'm saying here is that if lambda is repeating two times, okay, 0 is repeating. Suppose 0 is repeating two times. In that case, as you know that a minus lambda I into x equal to 0. If I write like this, okay, so where x is eigenvector, x will be the eigenvector, right? Any x which satisfy this is called eigenvector. Now, if lambda equal to 0, then as you know, this is as good as saying, what? Ax equal to 0, isn't it? It is as good as saying Ax equal to 0. Let me know if that is fine to everyone. Okay. So, so basically it was the eigenvector here. It was the eigenvector here. But now this is you can also say it is eigenvector. I mean, this is eigenvector corresponding to lambda equal to 0, that I completely agree. This is eigenvector corresponding to. But you can also say that if those eigenvectors, I mean those linearly independent eigenvectors are, let's suppose, 2, then can you tell me about the nullity? See, if this x is in this form, which means if it is ax equal to 0, then x is basically solution of a, right? Solution of ax equal to 0. So in that case, if you have two linearly independent eigenvectors corresponding to lambda equal to 0, it means you have two free variables, right? I mean, this is an eigenvector, but another way of saying it to lambda equal to 0, another way of saying is that if, let's suppose, don't worry about the eigenvalues, then another way of saying is that, or x is solution of ax equal to 0, right? This is another way of saying it. If x is, let's suppose, two linearly independent, and then that case, if you remember, we have done gate questions also. If x is represented like this, right? Maybe c1 plus c2, something like this. It means two free variable. It means nullity is 2. So basically, if x is like this, I mean, number of linearly independent vectors x will determine the nullity. So suppose in this case, if lambda is repeating two times, then in that case, basically this x, I mean, number of linearly independent eigenvectors, linearly independent x, could be 1 or 2, right? Is this fine? See, we talked about this particular thing in one of the video. If you are facing difficulty, then just watch this video. Do we have any relationship between rank and eigenvalues of the matrix? Okay. So just watch this video. If lambda is 0, then rank will be less than n. We can't say it is n minus 1, n minus 2, n minus 3. Which means as long as we don't know nullity, we can't say anything. Which means if lambda is repeating two times, then nullity could be 1, could be 2. Right? So basically, if lambda is repeating two times, then I don't know. I don't know nullity is 1 or nullity is 2. So that's why, if let's suppose A is n cross n, let me just ask you the question. Lambda equal to 0 is repeating three times. Then in that case, what will be the uh, rank of A? What are the possible rank of A? N, n minus 1, n minus 2, n minus 3. Just tell me. Okay. So see, if lambda is repeating, and lambda equal to 0 is repeating three times, right? Lambda equal to 0 is repeating 3 times. Then what does this mean? It means that uh, that the linearly independent eigenvectors could be 1, could be 2, could be 3, right? So linearly independent eigenvectors corresponding to lambda equal to 0. Okay, could be 1, 2, or 3, right? Which means n is not the possibility, because nullity could be 1, so which means nullity. Okay, nullity could be 1, which means it could be the answer. This could be the answer. So B, C, D could be the answer. So either answer is B or C or D. Okay, don't worry if you're not getting it, because I have already explained this in very good detail in one of the video. In this video, you just pause this video. Okay, in this particular video, I've already explained all of this. Okay, in all of this is in very good detail. So that's why I'm not repeating it. Okay. So, yeah, Anjali is saying that your way of breaking things down and connecting the dots makes everything clickable for me. So, thank you so much, Anjali. So, Anjali Kulkarni is giving a nice feedback. So, let me just, write it in the slides. So, thank you. Okay. Now, let's just see this particular question. For any matrix A, rank of a matrix is equal to number of non-zero eigenvalues. What do you think? So for example, let's suppose lambda is repeating 3 times, 0, 0, 0. Okay. Suppose lambda is repeating 3 times. 0 is repeating 3 times, then it is 5, 6, 7. Tell me the rank of matrix A. Okay. 3, 5, 6, 7, right? So, or maybe let me just call it 10, just to not have 7. So let's just see, this is 10. Okay. So 5, 6, 10. Tell me rank of A. So this is 3 and 3 is 6, right? So 6 minus, it will be either 1, or it will be 6 minus 2, or it will be 6 minus 3, right? So it could be 5, could be 4, could be 3. Number of non-zero eigenvalues are how much? 3. Is this always 3? Is this always 3? No, right? So this particular question is basically false, right? False. Is this okay to everyone? This is really, good question, and it should be understood to everyone. So what I'm trying to say here is that if you have lambda equal to 0 repeating 3 times, right? Then rank could be n minus. So basically number of non-zeros are just 3, right? So rank could be 3. I mean, that is fine, but it need not to be 3, which means it is 3 only if you guarantee, that number of linearly independent eigenvectors corresponding to 3 repeated. If it is repeating 3 times, then it is always 3. Okay, only if you guarantee that, okay, these are the 3 linearly independent eigenvectors corresponding to lambda equal to 0, then only it is 3. Otherwise, it is not 3. Tell me, can we guarantee? Can we guarantee for some metrics? What kind of metrics we can guarantee that AM equal to GM? What kind of metrics have this property that AM and GM are same? Yes, symmetric matrices, right? Okay. So basically, for the symmetric matrices, number of linearly independent eigenvectors are exactly n. And if it is repeating 3 times, you will be having 3 linearly independent eigenvectors. Okay. So AM and GM are same for symmetric matrices, but not for general matrix. So if you can guarantee that, okay, if it is repeating 3 times, then there will be three, you can say, linearly independent eigenvectors. For example, let's suppose lambda equal to 0 is repeating 2 times. And let's suppose this is 3, this is 9, this is 7, this is 8, like let's suppose 15. In that case, this is 6, right? In that case, what will the rank of A? 6 minus 1, or maybe 6 minus 2, right? Or maybe 6 minus 2. Could be, you can say, could be 5, could be 4, right? But for symmetric matrix, what is the rank of A? For symmetric matrix, can you tell me rank of A? Always 4. Okay, it is always 4. See, if you're not understanding that how I'm writing these things, I again suggest you to watch this playlist. Okay, this is the module 1, and we have covered all of this, right? I mean, I think I have covered this concept in 10 A and 10B. Okay, so just see this particular playlist, and 10A and 10B specifically. Okay, so here I'm just saying you that if you know that matrix is symmetric, then number of non-zeros are 4, and total are, let's suppose, 6. So basically then rank will be total minus zeros, right? I mean number of non-zeros. So basically, if you know that matrix is symmetric, then rank is number of non-zeros, isn't it? Can I say like this? See, this is total minus zeros, right? Zero is coming two times. It means number of non-zeros. Okay, see, let me just tell you what I'm trying to say. Let's suppose lambda is just repeating 0, 0, 0, 0 four times, right? And total is, uh let's suppose three more, okay? Okay. Asymmetric. Then can you tell me rank of A? It will be number of non-zeros directly. How much? Three. Why? Because rank of A will be total minus how many times zeros are repeating, because it is telling me number of free variables, right? Every zero is telling me number of free variables, 1, 2, 3, 4, because every zero is telling me number of linearly independent eigenvectors corresponding to lambda equal to 0, right? So number of free variables are 4. Okay, so basically number of pivot columns are 3 only. So this is number of non-zero eigenvalues. So basically, if someone asks me this question, that rank of a matrix is number of non-zero eigenvalues for any matrix A, then this is false. This is false. But if someone asks me this question, for any real symmetric matrix, rank of a matrix is the number of non-zero eigenvalues, then in that case it will be true. Okay. Because if it is repeating, let's suppose lambda is repeating 5 times or 10 times, it doesn't really matter. Okay. See, let me just tell you how many total lambda could be there. Obviously, it has to be square matrix. So n total lambda could be there, right? N total lambda. Okay. So basically, let's suppose, let's suppose this is the case. So what is the dimension of a matrix? Can you tell me? What is the dimension of the matrix? I think 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So I think 9. So dimension of the matrix is 9. ये टोटल नंबर्स कितने हैं? 9 है. उसमें से फ्री कितने हैं? Every lambda equal to 0 will tell you free. Okay, free columns. So 5 are free. So rank is pivot columns are 4. If A is symmetric. If A is symmetric. Is this fine? Okay. So in this case, this is true. If A is symmetric, then this is true. Otherwise, this is false. Okay. Now you might be thinking that why all of the sudden I'm revising these concepts. Can anyone just guess, random guess, that why I might be revising these concepts? So because I'm interested in the symmetric matrix actually. We have our symmetric matrices ready, right? A transpose A transpose. These are our symmetric matrices with me. We also find out eigenvalues of these things, right? Now, eigenvalues of this, generally we either you write lambda, or is this fine? I can also write eigenvalue in the square format, sigma square, sigma 1 square. Is this fine to you guys? Because ultimately we will find out the singular value after the square root, right? So I'm just saying it is sigma 1 square, right? So since it is a symmetric matrix, since it is a symmetric matrix, and if I'm finding the eigenvalues of this, can I not tell directly that what is the rank of this particular matrix A transpose A? If we know, okay, if we know eigenvalues, then we know um, rank of the matrix, right? I can directly say rank of, because A is symmetric. Let me know if that is fine to everyone. Okay, is this fine? Great. Now, now let's just see that why this rank of A transpose A is so, so nice to me. Why this rank of A transpose A is basically so close to what I'm looking for. Let's just see. So I will connect the dots, but let's just prove this very nice theorem that rank of A and rank of A transpose A is same. Let's just prove this. Suppose ये prove कर दिया. Okay, suppose somehow I prove it. Don't you think that it will be so powerful to connect all the dots? उसके बाद क्या होगा? उसके बाद let's suppose I know that rank of A and rank of A transpose A is same. Okay, suppose somehow I prove it, which we are going to prove in just 5 minutes. Okay, then I will do what? I will find out eigenvalues of this A transpose A. Those are nothing but singular values, right? So basically, since from this eigenvalues, whatever the non-zero eigenvalues are this, okay, I will get to know rank of A transpose A using those eigenvalues. I mean all non-zero eigenvalues, जितनी भी non-zero eigenvalues होंगी, उतनी ही non-zero singular values होंगी. Is this fine? Obviously, मतलब this is square root, right? So जितने non-zero यहाँ पे होगा, it's a one-to-one mapping, right? So उतना ही non-zero यहाँ पे होगा. So basically non-zero eigenvalues of A transpose A will be the rank of A transpose A, which is the rank of A, right? And non-zero eigenvalues is nothing but the non-zero singular values. So basically, by looking at the singular values, कि कितनी non-zero singular values हैं, okay, I will immediately get, okay, what is the rank of A? We will connect them. Okay, don't worry, we will connect them. So actually, once we prove this, it's going to be very nice. Okay, the dots will get connected. Let's just see that how those are going to connect. But let's just first prove this: the rank of A and rank of A transpose A is same. So anyone wants to give a try how to prove? Let me just tell you one thing. Suppose X is in the null space of A, right? X is in the null space of A. Then can I say X is in the null space of A transpose A? Tell me. Just think about it. See, let me just prove this. It is not very hard to prove. See, if X in the null space of A, it means AX equal to 0 अगर है, तो क्या A transpose AX equal to 0 नहीं है? Obviously है, right? So basically, you can say that if AX equal to 0, then you can multiply by A transpose both sides, and A transpose AX equal to definitely 0. So it means that null space, मतलब यहां से आप क्या बोल सकते हैं regarding the nullity also you can say that, or maybe regarding the null space, whatever you like to call, the null space of A is a subset of null space of A transpose A, right? मतलब जो यहाँ पे है null space में, वो सारे वेक्टर तो उधर तो हैं ही, isn't it? Let me know if that is fine. Now let's just prove other way. Okay, let's just prove other way. Which means let's just prove other way, which means that if X is in null space of A transpose A, okay, if X is in null space of A transpose A, then X is in the null space of A. Okay, just give it a try. Just spend 2-3 minutes in this. Okay, so let's just see if we can prove this. See here, if X is the null space of A transpose A, right, then A transpose A X must be 0, right? From this you can say X transpose AX must be 0. I mean, you're just multiplying X transpose both sides. Okay, just consider X transpose like a matrix. Okay, it might be a row matrix, but that's fine. Okay, it means you're just writing Ax transpose Ax equal to 0. Okay, maybe let me just go to the next page. See what I'm trying to say. See, let's just see the LHS part. Okay, let's just see the LHS part. Now here we are saying that X is in the null space of this, which means A transpose Ax must be 0, right? Now, let's just see the dimensions. So it is a column vector, right? Because Ax is a column vector, and if you multiply by this, then it must be a vector, right? Column vector. Okay. Now, if you multiply this column vector of zeros, right, by a row vector, let's suppose whatever the row vector, then you will be getting a scalar, right? Some zero is a scalar. Is this fine? I mean, this I'm not writing this is a column vector, but ultimately this is a column vector. And if you multiply with this some row vector x transpose, for example, then it will be a zero, right? Which is a scalar. ठीक है? Okay. So anyway, what I'm trying to say, let's just multiply, let's just multiply this by x transpose both side. X transpose Ax equal to 0. Here this 0 is a scalar, right? This time 0 is a scalar. Understood? This is nothing but Ax transpose Ax equal to 0. It means what? It means it is basically V transpose V equal to 0, right? It means what? A vector itself is orthogonal to itself. Is this even possible? No, right? So basically, it means that you can say this is mod of B, I mean norm of B square equal to 0. And from here, uh, if the norm of V square is equal to 0, it means norm of V equal to 0, right? And it means that V must be 0. It means that V must be 0. Why that is the case? Because norm of V is always A square plus B square plus C square, like this, right? If this thing is 0, okay, then individually these has to be 0. Okay. If some norm is 0, it means that individually the vector must be 0. So basically, anyway, like you can understand in any way, or maybe you can understand like this, that if vector dot product with itself is 0, is it possible that it is orthogonal to itself? Can the vector be the orthogonal to its own vector? Not possible, right? So that's why that vector must be 0. So from here you can say Ax equal to 0. Okay. Or maybe if you want to understand like this, then it is nothing but A square plus B square plus C square. If A square, if I mean if three positive numbers adding up to be 0, it means individually A is 0, individually B is 0, individually C is 0, right? Which means vector is 0 itself. Okay. So from here Ax equal to 0 we got. It means what? X is in the null space of A. Okay. Cool. So actually, this is very popular, and we will see the properties of A transpose A also. I mean, later on we will see the properties of A transpose A, and how it is relating to the rank of A and other things, because A transpose A, as I told you, is very popular and very needed matrix. So we will see more about A transpose A later on. But for now, is this proof okay to everyone? That if X is in null space of A, then it is in null space of A transpose A. If it is in null space of A transpose A, which means that A transpose Ax equal to 0, then from here we can definitely prove that Ax equal to 0. Okay. Aditya has written some other proof, which is also very, very nice. Okay. So actually, in one of the homework, we have given this as a proof. So Aditya has written very nice proof, some other proof. So if you want, you can try to understand this proof also, right? So what he is saying, that since S x belongs to null space of this, which means this, right? Which means this AX is in the left null space of A. Okay, AX is in the left null space of A, but AX is in the column space of A already, right? I mean, AX means it is in the column space of A. And AX, we have just proved that it is in left null space of A. Okay. And then from, the fundamental spaces that we know that, let's suppose it is a matrix, it is a vector, right? So let's suppose this is giving you 0. Okay, this is AX equal to 0. Then this row multiplied by this particular vector is giving you 0, right? It means what? It means what? We have already seen that row space of A is always perpendicular to null space of A, right? And if you take the transpose of this, then basically you can also take the transpose of this, then which means row space of A transpose is also perpendicular. I mean, this is true for any matrix actually, right? It is perpendicular to row space of A transpose is perpendicular to null space of A transpose. I mean, if it is true for A, then it is true for A transpose also. It means column space of A is perpendicular to left null space of A transpose, right? So Aditya is saying that since we have just proven that AX is in the left null space, and AX is anyway, by definition, it is anyway in the column space of A, right? So if something is in left null space and something is the column space, then it is not possible. It means it has to be zero vector. So AX must be zero vector. Okay. Sorry, this is left null space of A. Yeah. Thank you for correcting me. So this is left null space of A, not A transpose. Okay. So whenever you see any typo or either in saying or in writing, you just correct me so that later on people don't get confused. Otherwise, like people will send the screenshot in the Telegram group. They will ask that, okay, is this meant to be A transpose or this is meant to be A, like that, right? Okay, this is also very nice proof. Okay, so very nice proof. Okay, and this is some easier proof. By the way, on if you check on the Stack Overflow, okay, one of the answer, okay, I'm not saying all the answer, obviously, one of the answer had the easier proof that we just did. Okay, this particular answer, okay, this particular answer have this proof. So I have taken this proof from here. So basically, rank of A and rank of A transpose A is same, and which is obviously same as the transpose of this, because A and A transpose has the same rank, which is obviously same as rank of A transpose. Okay. So basically, now we know that rank of A and A transpose A, or A transpose, whatever you like to say, basically both are same, right? Okay. Now let's just see that how it is helping us to finding out the rank using the SBD. So we know, right? We know that singular values are nothing but square root of eigenvalues of A transpose A, right? If you take the square root of this, then it will be the singular value. You remember? So basically, you can say that non-zero, okay, since it is a symmetric matrix, non-zero, non-zero eigenvalues of A transpose A equal to rank of A transpose A. Is this okay to everyone? Why that is the case? Why that is the case? This equality is because A transpose A is symmetric. And since non-zero eigenvalues of A transpose A is same as, right? This is exactly same as non-zero singular values of A. Singular, I mean number of non-zero at least. Okay, this is basically number of, okay, number of non-zero singular values of A, because it's just a square root, right? And instead of this, I'm writing rank of A, right? I'm writing rank of A. So basically, rank of A is nothing but non-zero singular values of A. So for example, if, let's suppose, just an example. Yeah. So let's suppose that if they give me this as eigenvalue decomposition. Okay. So just a second. Suppose they give me this as eigenvalue decomposition. Tell me rank of A just by looking at this eigenvalue decomposition. Sorry, not eigenvalue decomposition, singular value decomposition. Okay. So this is singular value decomposition, not eigenvalue decomposition. So tell me rank of A. This is number of non-zero singular values, right? Number of non-zero singular values. So directly you can say number of non-zero singular values, which is two, right? Two. It is fine. So if you have your SBD ready, then you can directly tell the rank. And it is not just useful to tell the rank. I will show you it is very useful in many other cases also. SBD is actually very, very useful technique. Okay. Now, let's just understand this SBD more, and we will have many questions regarding the SBD. Okay, but my first goal is to understand the SBD. Okay, in its clarity. Once you understand this SBD in its clarity, then we will be having many questions, because actually the questions I was finding over the internet. Okay, they were interrelated to the SBD concept, which means that some questions were regarding the rank, some questions were regarding like this, some questions were regarding like this. So I thought that let's just first cover these topics, and then we can have at least 20 questions. Okay, 20 questions back to back regarding the SBD. I can say 20 to 30 conceptual questions. Okay, back to back. And I will take just one quiz. Okay, if you want I can take just one quiz for the SBD itself. Okay, if you want we can just put one quiz for the SBD itself, only for the SBD, one weekly quiz, so that this SBD is very clear to everyone. See, in the exam, they might not ask many questions just by SBD, okay, just by directly by SBD. But if you are practicing, if you are knowing this SBD more, then it may be possible that whatever they ask in linear algebra, maybe you can connect it with the SBD. Okay, many concepts are interrelated with the SBD. Let me just tell you, because it has no restriction actually. So you can view any matrix as a singular value decomposition, then you can think about that matrix. Okay. Anyway, let's just see the second topic. So rank of a matrix and SBD. I hope that's a little bit clear. Maybe we will do more practice, more examples. It will be more clear. But I hope it is clear. As of now, it is clear, right? So what is the conclusion here? That rank of A equal to number of non-zero singular values, right? Now let's just see that how we can view the singular value just like similar to eigenvalues, which means, so this is okay. This is done. Now, let's just see this particular topic, which is that viewing the singular value just like the eigenvalues. So, let's suppose A is a square matrix, right? Suppose A is a square matrix and eigenvalues are lambda 1, lambda 2 like this. Suppose, okay. Then in that case, you know that AX equal to lambda x. बहुत आसानी से हम लिख देते हैं ना AX equal to lambda x. In that case, you know that AX equal to lambda x, right? Is this okay to everyone? This is I mean popular equation for the eigenvalue eigenvector. What if X is a rectangle matrix? Okay, but what if what if sorry, A is a rectangle matrix. Okay, what if A is a rectangle matrix? In that case, obviously the eigenvalues doesn't even exist, right? So in that case, let me just write it. So obviously eigenvalues doesn't even exist, right? But still we want to write something like AX equal to lambda x. Can we do it? What do you think? Yes, actually we can do it, right? So still we want. First of all, tell me if A is M cross N matrix. Okay. Suppose A is M cross N matrix. Now let's just call it A into V. Okay. This is M cross N. This must be, if it is a vector, then it must be N cross 1. Then whatever vector I have here, okay, let's not worry about it, but whatever vector I have here, let's suppose U. This will be of what dimension? M cross 1, right? M cross 1, right? And then lambda. Okay. Instead of lambda, I'm writing sigma. So basically, I will just show you that AV1, okay, you can even write AV1 equal to sigma 1 U1 like this, right? You can even write like this. Okay. So basically here, V1 is the same V1 that we have seen, which is U sigma V transpose. यहाँ पे जो V1 आता है ना, V equal to, अगर if you say this is V1, this is the same V1, this is V2, like this, right? And let's suppose R is the rank of the matrix, or in other words, R is number of non-zero singular values. Okay, R is number of non-zero singular values. Let's just see why this is possible. Actually, that's very easy. Okay, there is, I don't know if it is worth creating that much hype or not, but it is easy only. Let's just see. Okay, see, A equal to U sigma V transpose, right? Can you also write, if V is orthonormal matrix, can you also write like this? Let me know. Let me know. Can we write like this? Yes, right? Okay, great. Great. So basically you can say this A is nothing but this also. From here, you can say A into V. Okay, you just write multiply. Okay, on the right, you multiply V and V. A into V equal to U into sigma, right? Okay. So what is this A into V? Maybe let me just, I think you might recall from eigenvalue decomposition itself. So basically this A into V is same as writing. Do you remember I have written A into V, if it is V is a matrix, right? V1, V2. This will be suppose M cross N. Then this is N cross N. Okay. A into V equal to A into V equal to U. What is the dimension of U? If it is M cross N, then U will be M cross M, right? So U, which is U1, U2, UM into sigma. Okay. What is the dimension of sigma? Can anyone tell me? Same dimension as A, right? So what is the dimension of A? M cross N. So it is also M cross N. Okay. It depends if M is more. Uh, if M is more, then maybe sigma 1, sigma 2, like this, right? Okay. Let's suppose number of non-zero are just sigma R. Okay. Number of non-zero are, let's suppose, just sigma R. After that, let's suppose everything is zero. Doesn't really matter. Okay. Number of non-zero, let's suppose sigma R. Is this fine to everyone? So here R is rank of the matrix, or in other words, number of non-zero singular values. Okay. Okay. Now, let's just go to the next page and let's just see that what we can do from here. Okay. So what we can do from here is that let's just multiply this. So this will be, do you recall that this will be same as a into b1? I mean, the first vector here will be a into b1. Is this okay to everyone? The second vector here will be av2. The third vector here will be like this and avn. Somewhere you will be writing avr, I mean the rth vector, right? And then you will be writing avr plus 1 and then avn. This is equal to, let's just see what it will be. Okay. This is m cross n matrix. This is m cross n. No, sorry, this is m cross n. Have we missed something or like this? Um, this V is n cross n, right? Yeah, that's fine. Okay, okay. That's fine. So earlier, no, that's fine. Yeah. So this was earlier, it was n cross n. Okay. But after multiplying by the a, this particular vector is m dimension. Okay. Which means the whole matrix is m cross n now. This was n cross n earlier. Now it is m cross n earlier. M cross n now. Why? This vector is in the Rm. Okay. I mean, if you multiply the vector which is in Rn by this a, then this vector is in Rm now. Okay. Anyway, that's fine. The dimension must match. So it is matching actually. Okay. I was just seeing that if it is matching or not. Okay. Now let's just see. Let's just see how we can write this. So see how many zeros are this? Many zeros. I mean, whatever. Like, I mean, all the zeros are here, right? So how to multiply a matrix with a vector? You very well know, right? So it will be sigma one u1, isn't it? Tell me, is the first vector fine to everyone? This is m cross m matrix. Okay. So this is sigma one u1, right? What is the second vector? Sigma two u2, right? Till sigma r things are fine, which means if it is non-zero, then sigma r u r actually till sigma r things are fine. But now if it is zero, okay, now let's suppose all are zeros. Okay, now let's suppose all are zeros. Then anyway it is zero, right? Then anyway it will be zero. So this particular matrix multiplied by the zero vector, it will be anyway zero. I mean, till sigma r things are fine, but after that anyway things are zero. Let me know if that is fine to everyone. So if it is m cross n, so ultimately it is m cross n. This is m dimensional vector. So these are the n vectors, right? These are the total n vectors. Okay, these are also n vectors. Anyway, so these are the n vectors total. These are also n vectors. But yeah, after some point in time, if these are the non-zero singular values are sigma are r, then it will be sigma r u r, right? थोड़ा समझ में आ रहा है? सी सिग्मा वन सारे जीरोज का मल्टीप्लाई होगा तो सिग्मा वन से मल्टीप्लाई होगा बाकी सब जीरो, राइट? सिग्मा टू का इससे मल्टीप्लाई होगा बाकी सब जीरो तो सिग्मा टू यू टू. इफ सिग्मा आर इज देयर तो सिग्मा आर का होगा यू आर से, ओके, बाकी सब जीरो. बट आफ्टर दैट सिग्मा आर एवरीथिंग इज एनीवे जीरो, राइट? सो एनीवे लाइक इट विल बी समथिंग लाइक दिस. नाउ इफ यू कंपेयर वेक्टर बाय वेक्टर, आई थिंक मैंने कॉम्प्लिकेट कर दिया. आई विल ट्राई टू सिंप्लीफाई दिस, बट लेट मी जस्ट नाउ कंटिन्यू ऑन दिस on the same line. So see, if you compare vector by vector, ab1 equal to sigma 1 u1, ab2 equal to sigma 2 u2, like this. Till how much? Till we are sigma r u r. After that, if you want, you can write. I mean, I don't have any problem, but it is zero actually. Okay. So basically, it is just another way of looking at the SBD. So what I'm saying here is that, see, we started with this, right? We started with this. Tell me, do we need any assumption to write from here to here? Any assumption, any sort of assumption. It is just a way of writing, right? We don't need any assumption. V transpose and V inverse are actually same because V is orthonormal matrix. Okay. Do we need any assumption to go from here to here? No, right? It's invertible. You can definitely write it like this. So it is just a way of writing. And finally, we found out that AB is nothing but sigma U, which means AB1 is sigma 1 U1, AB2 is sigma 2 U2, and so on till you are. Okay. So which means I can say till you are. I mean, if it is non-zero singular values, if you have a sigma non-zero singular values, then for the non-zero singular values, you can definitely write like this. ठीक है. अगर नॉन जीरो सिंगुलर वैल्यूज हैं तो यू कैन राइट लाइक दिस. R. If there are non-zero singular values, then these R equations hold. For rest, if you want, you can write, okay, A VR plus 1 also you can write, but it will be, can anyone tell me what it will be? Actually, because of these zeros, okay, because of these zeros, okay, A VR plus 1 actually got 0. Okay, there is no role of U to play. Okay, you doesn't mean the you. I mean, as a pronoun, it doesn't mean you. You means a symbol u or a vector u. Okay, not you. I mean, you have very good role to play in your rank. Okay. Okay, again, rank is not a rank of a matrix. Rank means gate rank. Okay, anyway, maybe a bad joke, but yeah, that's fine. So avr plus 1 is basically ultimately 0. Right? Understood? Avr plus 2 is also 0. Avr plus 3 till basically, I think there are n vectors, right? N v vectors. How many? Yeah, with the dimension there are n vectors. These are 0 vectors. ठीक है? Understood? Okay. So, I don't know why you people are quiet. Is this too hard to understand? We can revise. Don't worry, I will be revising. Okay, but at a first glance, is this too hard? A और B का मल्टीप्लाई करके ही, मतलब आई जस्ट लुक एट इट इन दिस वे, इट इज नॉट वेरी फैंसी, राइट? मतलब A B1 को सिग्मा 1 U1 बोला है इसमें. आई डोंट थिंक इट इज वेरी हार्ड. आपको इतना तो समझना पड़ेगा एक्चुअली. ओके. मतलब थोड़ा मशीन लर्निंग का आप कोर्स कर रहे हैं तो इट इज, मतलब आई मीन, मैं आई विल ट्राई टू मेक इट वेरी इजी, डोंट वरी. ओके, विद द मैनी एग्जांपल्स, विद द आई कैन से विद द step by step procedure. I will try to make it easy, but just you also try. Okay, see, it will be both ways. You also try to make the things, if it is looking little complicated, then you also try to make it understand. Don't just immediately give up कि नहीं, अब तो मतलब मैंने सोच ही लिया है कि समझना ही नहीं है. ऐसा नहीं करो. ठीक है? अगर थोड़ा कॉम्प्लिकेटेड दिख रहा है, एक बार तो समझ के देखो. हैव पेशेंस, डोंट वरी. हम क्वेश्चंस करेंगे. वी विल बी, एज आई टोल्ड यू, एक वीकली क्विज होगा एसबीडी का. देर विल बी 20 होमवर्क क्वेश्चंस. 15-20 वीकली क्विज में होंगे. 40 क्वेश्चंस के बाद तो एसबीडी का मतलब मतलब होगा ही, मतलब पोस्टमार्टम हो जाएगा एसबीडी का. तो आपको अच्छे से समझ में आएगा. इतना ऐसा नहीं है कि आपको समझ में नहीं आएगा, बट यू जस्ट ट्राई. ओके, अगर कुछ कॉम्प्लिकेटेड दिख रहा है तो एक बार उसको आप अपने से ट्राई करो. ठीक है? तो A B1 सिग्मा 1 U1 के बराबर है. आफ्टर सम पॉइंट इन टाइम, एक्चुअली इफ इट इज जीरो, यू कैन से सिंगुलर वैल्यूज, तो फिर U डजंट हैव एनी रोल टू प्ले. ओके, अगर वो UR है तो UR करस्पॉन्डिंग टू सिग्मा R. फिर उसके बाद, ओके, इसके बाद ऑल दीज गेट वेनिश्ड. वेनिश इन द सेंस, मतलब वो इक्वेशन में नहीं है, बाकी मतलब वैसे तो है. सो फाइनली दिस इज द सेट ऑफ इक्वेशंस वी आर गेटिंग. ओके, वेरी नाइस स्लाइड वी हैव. We can infer many things here. Tell me, tell me, from the day one, don't you know that, I mean, day one of the SVD, that U1, U2, UM, let's suppose these are orthogonal, right? From the day one, you know, right? Similarly, from the day one, you know that V1, V2, Vn, let's suppose these are orthogonal. Okay. Now you tell me, Now you tell me that what is the rank of the matrix? If there are r non-zero singular values, then what is rank of A, assuming r non-zero singular values? Yes, this is r definitely, right? Okay. रैंक का मतलब सबको समझ में आता है, नंबर ऑफ लीनियरली इंडिपेंडेंट कॉलम्स, नंबर ऑफ लीनियरली इंडिपेंडेंट रोज, लाइक दिस, राइट? नंबर ऑफ, हाँ यही है ठीक है, लीनियर इंडिपेंडेंट कॉलम्स, लीनियर इंडिपेंडेंट रोज, ठीक है। और मे बी डायमेंशनलिटी ऑफ द कॉलम स्पेस, डायमेंशनलिटी ऑफ द रो स्पेस, अदर वेज ऑफ सेइंग इट, ठीक है। जस्ट लुकिंग एट all of these equations, just looking at all of these equations, can you not say that u is in the column space of A? Tell me, is u in the column space of A? What do you think? Right? By definition, you can see, right? U is in the column space of A. In the column space, if U's are in the column space of A, in the column space, you have R U's. And you know these are orthogonal, right? Can you not say you have just found out the basis of column space? See, in the basis, there will be R vectors. How we know? Because rank of A is R. R होंगे, इतना पता है। बेसिस मतलब लीनियरली इंडिपेंडेंट होने चाहिए, ऑर्थोगोनल तो वैसे भी लीनियरली इंडिपेंडेंट होते हैं। हमें आर यू मिल गए, ठीक है, कॉलम स्पेस में, एंड हमें पता है वो ऑर्थोगोनल है, तो वो बेसिस भी है। आर यू कनेक्टिंग द डॉट्स? So basically, from this equation, we got to know that u is in the column space of A. U2 is also in the column space of A. You are in the column space of A. In the column space of A, we have got how many vectors? R vectors. Those are linearly independent. एंड आर से ज्यादा हो नहीं सकते क्योंकि कॉलम स्पेस की डायमेंशन ही आर है। तो कॉलम स्पेस का बेसिस कांट वी से द ऑर्थोगोनल बेसिस वी हैव गॉट u1 to ur, right? Similarly, we know the rank plus nullity is equal to number of columns. Number of columns are here n, okay, in A, okay, in A की dimension m cross n, I'm assuming, okay. So nullity, can you tell me how much is the nullity? N minus r, n minus r, right? Now how many are these vectors? N minus r vectors. Are these vectors in the null space of A? Yes, definitely. Right? These vectors in the null space of A. You have such n minus r vectors. N minus r vectors you got in the null space of A. And fortunately, those vectors are also orthogonal, which means we have just found out the basis of null space also. So SVD is giving you too much, okay? SVD is giving you basis of column space. SVD is giving you basis of null space. SVD is also giving you, I will tell you, SVD is also giving you the remaining two. What are those remaining two? Basis of, just by looking at it, I will tell you, just by looking at it, you will get to know the basis of row space, basis of left null space. SVD is giving you everything you require, okay? 4 fundamental subspace, you can directly get through the SVD, right? Okay. So basically, we will come to that topic. I think I'm just going ahead of the time which I planned. So basically, I have that as a special topic. So I will talk about this 4 fundamental subspaces using the SVD, right? Okay, so Tejas Singh, now I understand why SVD is important for ML. It provides a whole context of LA. Actually, in linear algebra, whatever concept you can think of, okay, starting from system of linear equation to linear transformation, change of basis, or whatever concept you can think of, almost all the concept I can say is related to SVD. Almost everything is related to SVD. क्योंकि SVD किसी पे भी लग जाता है ना, देर इज नो कंडीशन ऑन SVD, किसी पे भी लगता है। तो वहां से सब कुछ निकल जाता है, कॉलम स्पेस, सारे 4 फंडामेंटल स्पेसेस यू कैन गेट फ्रॉम एसवीडी, रैंक यू कैन गेट एनीथिंग, ओके, यू कैन सॉल्व सिस्टम ऑफ लीनियर इक्वेशन आल्सो फ्रॉम द एसवीडी, ऑल्दो इट इज नॉट रिक्वायर्ड इन अवर सिलेबस, अगर चाहिए तो मतलब वी कैन डिस्कस अबाउट इट, बट या वी कैन सॉल्व सिस्टम ऑफ लीनियर इक्वेशन यूजिंग द एसवीडी, तो दैट्स वेरी पावरफुल मेथड. Okay. So anyway, let's just go back and let's just see what we were visualizing. Basically, we were here, right? We started from this, and the idea was this, that I want to visualize those singular values just like eigenvalues, right? Which means I want to write something like a b equal to, obviously it is not possible to write lambda b because it is not a square matrix, so maybe some lambda or some scalar into some u, right? And dimension we can figure it out, that a b equal to sigma u, it could be something like this, okay? I wish I can write like this, and svd is here to rescue us or to help us. So basically svd is saying actually we can write, if these are the r singular value, r non-zero singular values, then this kind of equations are possible. Let's just quickly prove that how these kind of equations are possible. We have started with the svd, right? And then we have said that okay, this v transpose is nothing but v inverse, and then we wrote like this, and from here it is actually not very difficult to see that ab, okay, just like a eigenvalue decomposition, it is just like eigenvalue decomposition, that ab, I'm just going the reverse process, you can say, okay. Now from here I'm just figuring out ax equal to lambda x, right? याद है x इक्वल टू lambda x किया था, ये x का मैट्रिक्स था, this was matrix of, sorry, or if you want you can write x lambda, okay, this was the matrix of x, this was the matrix of x, this was the matrix of lambda. It's just like I'm doing in the reverse way, okay, just to make sure that you I mean this is the way actually, मतलब ऐसे ही करना पड़ेगा वो. So a v को ऐसे लिखा, and we know that you can multiply a matrix with a column matrix like this, okay. So a into b1, the first vector will be a into b1, a into b2, this and this. So if these are sigma r singular values, so after some point in time it will be 0, and then you can write like this, okay. So at least you understood that okay, there are r equations which exist like this, right? And then remaining n minus r equations could be like this also, okay, if you want. Otherwise it's not very much of use for now, okay, but yeah, these are the r equations, right? Now let's not talk about the 4 fundamental subspace, it is even more interesting, but first let's just finish this topic and then we will talk about the 4 fundamental subspaces, right? How we can get those using the svd. Okay, but for now let's just focus on these set of r equations. Do you remember that I was talking about one thing here? See, here I was saying that this third step, okay, that finding the a transpose and then ui's are actually not very much required, right? Ui's can be found out using the shortcut. Now let's just see what is the possible shortcut here. I don't want to calculate this ui like this. Okay, I don't want to calculate this a transpose, but I want to do something else. Okay, using these set of equations, can you at least tell me what is u1? U1 is a vector which is 1 upon sigma 1 into a v1. If you have v1 from this step number 1, can't you directly calculate u1? If you have v1, you have sigma 1, u1 और sigma v1 और sigma 1 दोनों हैं step 1 and step 2 से, तो can't you directly get this u1 using this equation? So basically instead of this, let me write like this, okay, that u1 I can find out, u2 I can find out like this, right? Okay. Now, if you remember again, there was a question I was saying ki in this question they are playing some trick, right? Let's just see what trick they might have played. See here, they're calculating u1 as ab1 they are calculating, right? And then they're writing ab1 as sigma 1 v1, sigma 1 u1, and then they're directly calculating u1 from here, isn't it? So in the third step, right? In this third step, you don't actually need to find uij like this. Are you getting a little bit? So let's just solve. Okay, let's just solve some question. Maybe you will get to understand more. Let's just find the singular value decomposition of this. Yes, so Tejas is asking very good question. Tejas is saying कि R तक तो ठीक है, UR तक तो ठीक है. Okay, yes, so UR तक तो ठीक है. What about UR plus 1, right? What about UR plus 1? Because in that case sigma R plus 1 is actually 0. Yes, you can't find like this. I mean, from this you can't find, but some help you can get. So how to find the remaining use? Let's just see. Okay, let's just see how we can extend the basis. So this is called extending the basis. Okay, I mean, we have R vectors in the basis. Can we extend that basis? Okay, and then finally, find the perfect basis for the given subspace. So we will see if we can extend the basis or not. But for now, it is fine that you have got till you are at least you can get, right? Till you are at least you can get. So let's just do one thing. Let's find out the eigenvalue decomposition of this. Let me just help you with A transpose A and sigma. एक बार ये आप करके देखिए. Okay, if A transpose A is this, sigma is this, you just find out the V's eigenvectors of A transpose A. Maybe that is on the next page. Eigenvectors of A transpose A and the U's, right? Let's suppose this is V. ठीक है, तो by the way, this question I've taken from Berkeley University, and they have taken from Seeley. So Seeley is one of the book, one of the popular book. Let me just tell you. So they are saying David Seeley. Okay, David Seeley is one of the popular book for linear algebra. They have taken from Seeley, a Ley's book, and I have taken from that university. Okay, that's fine. So suppose that you have got your A transpose A, you have got these eigenvalues, and then finally the singular values. Okay, and then you are getting v1, v2, v3. Okay, so how many u's are there? What is the dimension of u? How many u's are required? In this particular case, u1, I think it is u1 and u2 only, right? Okay, u1 and u2. Fortunately, fortunately, you have two non-zero singular values. So in this case, you don't need to find u3, but we will see example where we actually need u3 also. Okay, so what is the u1 here? U1 will be 1 upon sigma 1, which is this value, into into v1, right? This will be 1 upon sigma 2 into a into v2. Okay, I mean, the calculation I'm not doing, but yeah, the answer I have, which is this, right? 1 upon sigma 1 a v1. It is basically u1. This is u2. Since u is 2 by 2 matrix, we do not need any more columns. Okay, so fortunately, okay, I mean, just a sigh of relief, you can say that fortunately we don't need any more column, right? So if a had only one non-zero singular value, then we would have to add another column to u to make the orthogonal or orthonormal matrix. So here it is 2. Okay, here we have got two non-zero, but as they are also saying that if a is just having one non-zero, then something else we have to do, right? We need to extend the basis. So to conclude, we have found out the singular value decomposition like this. So here, no much extra calculation. This is just a simple example, I can say, where, I mean, sweet spot is there. Number of non-zero is actually m, right? I mean 2, and you need only 2 u's. So that's why, I mean, things were in our favor. Okay? But as a first example, have you understood that what we are doing? Right? Okay. Now let's just do some more example where it might be the case that we are not getting exactly, 3. So here I think there's a 3 rows, so we need 3 U's. So let's just see. Let's just see. Okay, some people, instead of some university, some notations, basically I've taken this from this University of Otaha. Okay, so they are writing A star. Some people write A star, some people write A transpose. So maybe A transpose is more common, but that's fine. Okay, so A transpose, if you find out, so sigma 1 sigma 2 हो गया. हाँ, हाँ. Actually, here we need three U's, but we are just finding, I think, only one, two, sigma 1, sigma 2. Okay, we can verify. That's fine. This is, yeah. So actually, don't worry about it. This is called reduce or something. So let me just remove this. So basically, this is just two U's. You can say this is just two U's that we have got, but we need more U, right? We need more U, and we need U3 also. So we need some U3. Now, what they are saying that U1, U2 we have got theoretically, and we have also verified that okay, U1 and U2 are actually perpendicular to each other. Okay, we can anyway verify. Now we need U3 also. So what they have done, they have written this U1, they've written this U2, and now they are saying that by inspection, okay, I mean there is no method they have used. They are saying intuition, okay, here ये U3 में क्या लगाएं? By inspection only they have found the U3, which is okay. I mean, using the inspection, but there are ways to extend the basis, which we will see. Okay, we will see later on, and that's where the Gram-Schmidt process is required. Okay, but currently they are just using inspection. So this example is just to tell you that there might be the case that you need U3, but you don't have sigma 3. So let's suppose you don't know anything. What is the way? You don't know anything. Then find the eigenvector of A transpose, right? कुछ ही नहीं आता तो ए ट्रांसपोज का आइगन वेक्टर निकाल दो, हो जाएगा. ठीक है, इट्स नॉट एन इशू. Understood? But we can see, okay, we can see other ways if you want to calculate this U3 and all. I think it won't be required for the for our purpose most probably. I just wanted to let you know that this U1, U2 are there, but we can see optionally. Okay, I can take one optional lecture where I can talk about this extending the basis and these things, right? Okay, but yeah, it is fine. It is fine that you can at least calculate U1, U2. I mean, till you are at least you can calculate, right? Till you are you can calculate. Yeah, Aditya is asking that just with respect to zero. Yes, yes, right. So with respect to zero only, you need to find u's, right? Because non-zero singular values you have already taken. Zero singular value means zero eigenvalue, right? So I think with respect to zero only, yes, with respect to zero only. Okay. Yeah. Yes. So basically, we need to find, Aditya is saying, we will actually cover this in more detail. But as Aditya is saying, I'm just writing, we need to find null space of A transpose. Okay. Null space of A transpose. So let's just do one thing. Maybe I can connect all of these four fundamental subspaces and then geometry of SVD. Okay. So how this SVD makes sense geometrically, and what are these four fundamental subspaces? How to extend the basis and these things. Okay. We can talk about it in tomorrow's lecture, and then we will be having one more lecture where we will be doing back to back many questions regarding the SVD, so that everything get connected in your mind. Okay, so it gets so stuck that you never forget this SVD. And then we will be having just one special quiz for the SVD itself. Okay, so let's just do this. So we will continue from tomorrow for the four fundamental subspaces. Okay, so thank you everyone, thank you so much.